Okay. All right. We'll begin. We'll take a look. I hope your group projects are going well. I will post on Friday. I will have a sign-up sheet, okay, for time slots for your group to do final presentations. So final presentations will take place during week 10 and week 11. And your meetings will be 1 hour long. And so I'll have kind of a sign-up sheet where your group can sign up. It'll be first come, first serve on the sign-up sheet. So I'll probably post it on Friday. I don't know, maybe Friday at like 11 a.m. or something. I don't know. I'll figure out a time and I'll make the sheet go live at that time. I will offer extra credit for certain time slots. So basically, I don't want to be here like week 11 Friday or something, during finals week on Friday. So I'll offer kind of some extra credit, for some of the earlier time slots to kind of encourage it and groups to sign up for earlier time slots. So some of the time slots will come with extra credit, and just kind of make sure with your group that you guys can make it. The requirement will be that at least almost everyone. Okay, so everyone has to be at least present, and no more than one person will be remote during the thing. So if like one person is like, I can't physically be there for whatever reason, but I can kind of sign in via Zoom, and that will allow that. But your group has to be present to for the thing. Okay, so anyway, that sign up sheet will go live on Friday. Again, some groups have come by during office hours, and my hope is that the visits to office hours are helpful. Hopefully I'm able to kind of provide a little bit of guidance in terms of like, okay, what is your graphic trying to convey, and think, to help you think about some of these things. Some groups haven't come by at all, so I hope your things are going well there. Okay, I wanted to take a look at this topic of kind of identifying outliers. This is something that could be useful or interesting for your project, and just also in general, is this idea of like, okay, what is an unusual observation? Would you consider these observations to be outliers? And there's a few ways for us to consider what things are outliers, what observations are unusual. And so, but in order to kind of understand outliers, we have to be able to understand this concept of variation or spread, right? And so when we're talking about numeric values, variation, let me slide that over. Variation is this idea of, how similar are the values to each other, or are the values, kind of very different from one another. So if you imagine these three rooms, okay, and you think about the ages of the people in the rooms, we have different amounts of variation. So if you imagine the second grade classroom, the students in the second grade classroom, all the students in that classroom are probably going to be age 7 or age 8, okay? So almost everybody has like the same number there for their age. Think of a college classroom, okay? In a college classroom, people are similar age, but you have a little bit more range there, right? 18, 19, 20, 21, 22, something around there. And then, of course, you're going to have some students, maybe some non-traditional students that are outside of that range, students who've come back after, maybe military service or working or taking a year off or things like that. Imagine going to like the urgent care, urgent care office, or maybe like the DMV or something like that, and think of the waiting room. and what are the range of ages there. And if you go there, you're going to have all kinds of ages, right? You got babies, young children, teens, adults, seniors, things like that, right? So in this case, we would say the second grade classroom has the least amount of variation. The college classroom has medium variation, and originally I wrote DMV waiting room, but then I changed it to urgent care office. That would have the most amount of variation, right? And instead of just saying we have little variation to lots of variation, we have numeric quantities like the variance and the standard deviation. These are ways for us to actually quantify the amount of variation. We have the range and the IQR as well, okay? The definition for variance and standard deviation, we can think of the variance as the, quote, average squared distance from the mean. The symbol we use for the variance is s squared. The standard deviation is the square root of the variance. And so the symbol for that is just s, okay? So variance, average squared distance from the mean. The mean is, like kind of this, a middle value here. And so the formula for the variance is given by this, x minus x bar. X is each value, x bar is the mean, all right? And we're going to take each value, subtract off the mean. That's going to give us the distance from the mean. And then we're going to square it, okay? And then we take the average, which means add them up and divide by how many you have. But I put average in quotes because we add them up. That's what the summation sign here is. Add them up, but then we're going to divide not by how many we have, but one less than that, n minus 1. Okay, so that's the variance, the average squared distance from the mean. Standard deviation is the square root of the variance, so it's the exact same formula, but just inside a square root. When you use the computer, you basically ask the computer to just calculate the variance and standard deviation. But I'll just show you a couple examples by hand of calculating the variance and the standard deviation. Okay, so let's say we have these numbers 1, 2, 3, and 10. Okay, the variance we can think again is the average squared distance from the mean. And so, what's the mean of these numbers? 1, 2, 3, and 10 add up to 16. I've got 4 numbers. I do 16 divided by 4. The mean is 4. Okay. So the next part is to find what is the distance each point is from the mean and square that distance. So because we're looking at squared distances from the mean. So 1 is 3 units away from 4, and you square that, you get 9. 2 is 2 units from 4, you square that, you get 4. 3 is 1 away from the mean of 4, and you square that and you get 1. And then 10 is 6 units away from 4, and so that square distance is 36. So our square distances from the mean is 9, 4, 1, and 36. And then we take the average. So we would add up 9, 4, 1, and 36. That adds up to 50. And we are going to divide not by, we wouldn't do 50 divided by 4, we do 50 divided by 3. The reason, it's known as Bessel's correction. If you are a statistics or data theory major, you will prove why we use n-1, and it's because it becomes an unbiased estimator of this and that. But that's in a later course. And if you're not statistics or data theory, then you don't have to worry about it. But yeah, we're going to divide by n-1 rather than n. So we add them up, we get 50 divided by 3. We get a variance of 16.667. Okay. All right. Is that okay? This concept of variance as an average square distance from the mean. And so we can see that, when the numbers are more spread out, you have the mean, your distances from the mean are going to be greater. And so you'll have a greater variance. If the numbers are very similar to each other, the distances from the mean are going to be a lot smaller, and you'll have less variance. Okay. Standard deviation is the square root of the variance. So if the variance is 16.667, standard deviation is going to be 4.08, right? Square root of that. Okay. The command in R is you just call variance or standard deviation on your vector. So here I make a vector with the numbers 1, 2, 3, and 10. Variance of x, 16.667. Standard deviation of x, 4.084, 4.0824. Okay, so these are the commands: var x sdx to get your variance and standard deviation in R. Just kind of another example here. Let's say we have two families. Both families have 5 children. And in both families, the mean age of the children is 9. Okay, so you go, okay, we've got 2 families. Both families have 5 kids. Both families, the average age is 9 years old. Okay, are these 2 families similar? Well, we have the Baker family and the Cook family. I just made up these names here. Okay, so let's say in the Baker family, the kids' ages are 1, 3, 9, 13, and 19. And if you add those up, indeed, the average age is going to be 9. Okay, so all of these things add up to 45 divided by 5. The average age is 9. Okay, Cook family, the ages are 7, 8, 9, 10, and 11. Right. So does life in these 2 families look similar? I would say no. Right. It's very different. Right. And the Cook family, everyone's kind of very similar in age. In the Baker family, the oldest is much older than the youngest, right? This 19-year-old is probably doing, helping out with, babysitting and things like that. Just looking at the ages, we can see, the ages in the Baker family are more spread out than they are in the Cook family. Mentioning only the number of children and the average age doesn't give us the complete picture for the values here, right? We need to kind of have a measure of like how spread out these are, how much variation there is, or what's the variance, what's the standard deviation. Okay, so just kind of very quickly, here's kind of the manual work for getting the squared distances from the mean for the Baker family, right? So if our mean is 9, our distances would be 8, 6, 0, 4, and 10. And when you square those, you would get 64, 36, 0, 16, and 100. The average of those is you add these up. Again, average in quotes, we have 5 squared distances. We add them up and divide by 4. We get a variance of 54 and a standard deviation squared of that standard deviation is 7.34. Okay, and again, I can just type this into R. It's very simple. I just create a vector 1, 3, 9, 13, 19, and I say what's the standard deviation, and it gives me 7.34. Okay. So this is what we get for standard deviation of ages in the Baker family. Very similar steps for the Cook family, but very different numbers, right? So in this case, our numbers are 7, 8, 9, 10, and 11. And so if the mean is 9, 7 is 2 away, 8 is 1 away, 9 is 0 away, 10 is 1 away, and 11 is 2 away. And so when you square these, you get 4, 1, 0, 1, and 4. And so when you add these up, they add up to 10. You divide by n minus 1. Our variance is 2.5, so much less variance, right? And the standard deviation here, when you take the square root of 2.5, you get 1.58. So, obviously, we could just look at these 2 sets of numbers. We can look at the Baker family and the Cook family, and I can say, okay, there's more spread in the ages for the Baker family, less spread in ages for the Cook family. But now we're able to quantify this specifically. And we can say the standard deviation of ages in the Baker family is 7.348. Standard deviation of ages in the Cook family is 1.58. And this quantifies the amount of variation, which is useful because there's going to be a lot of data sets where you have so many values. And you want to just kind of be able to measure how much variation there is without necessarily having to look at every single number yourself. Okay, so rather than just saying the ages of kids in the Baker family are more spread out, we can quantify it, and we can say the standard deviation is 7.35 versus 1.58. Okay, let me go ahead and give you your first view quiz answer, which is the letter A. A as in apple. A is your first view quiz answer, A. Okay, let's let's load up the penguins data set. I don't know how we feel about the penguins data set or the questions there, but here it is. All right, and let's. So I've loaded it up, and so again, so in the penguins data set, we have 3 different species of penguins. We got the Adelie penguins, the chinstrap penguins, the gentoo penguins. Okay, and then we've measured different things like the bill length, the bill depth, the flipper length, and the body mass. Okay, and so we want to let's just take a look at some of these things. There's other variables, and so let me look at bill length and bill depth. I'm going to pivot these longer, and I'm going to make a histogram out of these. Okay, and we're going to color the histogram differently based on which variable we're looking at. Okay, and so here is the histogram of all the bill depth measurements. Here's the histogram of all the bill length measurements. Okay, and so visually, which we can see, which variation. I'm sorry, which variable has more variation, right? Which variable has a greater standard deviation? What would you say? Okay. So yeah, bill length, right? We can see the spread, in values for bill length is greater, right? If we say, okay, we got values as high as, about 60, values as low as, 32, 31. Okay, so we got quite a bit more variation. If we look at bill depth, okay, there is less variation. And so, visually, this is what we see, and we can measure it, right? So I can just take penguins and do summarize, and I can say, give me the mean depth and the standard deviation of depth, okay? And we see, okay, the mean is around 17.2, that's around the middle, and the standard deviation is 1.97. The mean length is 43.9, around 44, and the standard deviation is 5.46. So numerically, we do indeed see that there is a greater standard deviation for the length than there is the standard. This value, standard deviation for length, is higher than standard deviation for depth. Okay, so that's what we see here. So when we want to talk about how unusual a value is, a useful measure is what we call the z-score. The z-score tells us how far something is from the mean, the distance from the mean, except it's expressed in standard deviations. So we don't just say, this penguin has a bill depth that's 3 millimeters above average, okay? So, the average bill depth is, some number. We don't just say this penguin has a bill depth that's 3 millimeters above average, but we say this penguin's bill depth is 1.5 standard deviations above average. Okay, so we take the met distance, which is going to be x minus x bar. That's the distance from the mean, and then we divide by the size of the standard deviation. So if our standard deviation is around 2, right, and we have a penguin with a bill depth of, say, 20.2, its z-score would be around 1.5 because each standard deviation is 2. 20.2, this penguin is 3 millimeters above average. You divide by 2, that's about 1.5 standard deviations. Okay. If a penguin is 4 millimeters above average, then it has a z-score of around 2. And if a penguin has a bill depth 6 millimeters above average, then it has a z-score of around 3. It's around 3 standard deviations higher than the average. Okay. Whereas if we're looking at bill length, being 6 millimeters above average is only around, just over 1 standard deviation above average. Okay, because there's more variation for bill length. So the numerator again is how far an observation is from the mean, and we divide by the size of the standard deviation s to see how many standard deviations we are from the mean. And this is useful to help us kind of compare values from different sets of data. Okay. So here's a question: which penguin is more unusual? Is it more unusual to find an Adelie penguin with a bill depth of 20 millimeters, or a Gen 2 penguin? I don't know how to pronounce this. Gen 2 penguin with a bill length of 55 millimeters. Okay, and right now we can't answer this, right? We don't know enough about penguins to be able to answer this off of the top of our head. So we need to have our penguin summary statistics here, okay? So here I say let's group by the species and let's calculate the mean and standard deviation of bill depth. Let's calculate the mean and standard deviation of bill length, okay? We have to get rid of our missing values. We do na.rm equals true. All right, so for the Adelie penguins, the mean depth is 18.3. Our standard deviation is 1.22. Okay, and then and so we want to know, okay, an Adelie penguin of 20 millimeters is above average. How much above average? Okay, and for a Gen 2 penguin, okay, its bill length of 55. How how different is that? Okay. And so we want to kind of take a look at that. So for the Adelie penguin, we're going to take the mean of 18.3 and the standard deviation of 1.22. Okay, and we're going to do 20 minus the mean is 18. I got a few more decimals. 18.346. And standard deviation, I had a few more decimals, 1.217, okay? We get a z-score of 1.359, so we're around 1.359 standard deviations above average, okay? The Gen 2 penguin, we have a bill length of 55 millimeters, so we're going to subtract off the mean of 47.5, and we'll divide by the standard deviation of 3.082, and we get a z-score of 2.433. So by looking at these two z-scores, we can say, okay, the Gen 2 penguin is further away from the mean than the Adelie penguin. So the Gen 2 penguin with a bill length of 55 is more unusual than the Adelie penguin with a bill depth of 20 millimeters, right? It's farther from zero as far as its z-score. Its z-score is farther from zero than the other one, right? And so this would be the more unusual observation. Just keep those numbers in mind: 20 for bill depth of Adelie and 55 for bill length of Gen 2. I can create a plot with, so I got a histogram, and I'm going to create a facet grid based on species. And so here's the Adelie penguin, and we can say, all right, so here's bill depth. How unusual is a bill depth of 20 millimeters versus for Gen 2, how unusual is a bill length of 55 millimeters? Okay, so 55 millimeters is out here for the Gen 2 penguin, and 20 millimeters is out here for the Adelie penguin for bill depth. Okay, and so it's a little bit hard to just kind of eyeball based on this, right? A 20 millimeter bill depth for Gen 2 would be very bizarre, okay, but it's not that weird for an Adelie penguin, okay. And 55 millimeter bill length for Adelie would be very, very extreme, okay. And here, there are observations. It's still extreme, and it's more extreme than the 20 millimeter for the Adelie, right? So we're kind of, you have to do something like this if you're trying to compare, apples to oranges, right? If you're trying to, you can't just say, okay, 20 millimeters is higher, than over here. You have to kind of look at it relative to its own group. So we have to do that, okay? just to kind of further emphasize my point, I can go through the actual values in the data. All right, so here I'm going to take penguins. I'm filtering it to Adelie species, and I'm going to create a new variable that says depth over 20, okay? And this is going to be equal to the result of this comparison. I'm going to take build depth millimeters greater than or equal to 20, and so this will return either true or false, okay? If the build depth is equal to 20 or higher, greater than or equal to 20, it's going to return true, and if it's not, it's going to return false, right? And so, so after I create this variable, I can just select that one variable, and then I can create a table, all right? And so what this says is, in our data set, out of all the Adelie penguins, 18 of them have build depths of 20 or greater, and 133 of them do not. Okay, so we could see, it's not very common for an Adelie penguin to have a build depth over 20 millimeters, but we have 18 examples of such. Okay, and similarly, we do the same thing for the Gen 2 penguins. I'm going to say, let's filter to just the Gen 2 penguins. I'm going to create a new variable, length, bill length over 55, and we're going to just do bill length millimeters greater than or equal to 55. And I select that variable, and I say make a table, and it says, okay, there were 120 Gen 2 penguins that did not have bill lengths over 55, and we had 3 where it was 55 or greater. Okay, and so we can see, indeed, it is more rare to encounter a Gen 2 penguin with a bill length of 55 or greater than it is to find an Adelie penguin with a build depth of 20 millimeters or greater, right? So all of these things just kind of confirm what we've been seeing, which is 55 millimeter bill length is more unusual than the 20 millimeter bill depth, okay? At least for the Adelie penguins versus the Gen 2. This could, you could further do it and just say, what's more unusual? A female Adelie penguin with this bill depth, or a male, Gen 2 penguin, you could kind of ask all of these things and say, hey, how unusual is this particular observation, right? Because one of the things we observed if you look at the penguin data set is, the size of the female penguins and the size of the male penguins, there's overlap, but overall, if you take the averages there, they are a little bit different from each other. Okay. All right, and so that's one way for you to kind of compare observations from different groups by comparing it to its own group average and calculating the standard deviation within the group. Okay. All right, let me give you your second view quiz answer. Second answer today is the letter B. B as in bear. Okay. Just a general note about z-scores is if you look at a normal distribution, and if you have data that's unimodal and symmetric, so, plotting this, this I would say is unimodal and symmetric, and, most of these, this is unimodal and maybe a little bit skewed, and I don't know what happened here. There's like a little dip here, but, these over here look like they're fairly unimodal and symmetric. Unimodal and symmetric means there's one peak. Symmetric means, the shape is kind of looks, the left-hand side and the right-hand side look kind of similar. If your data is mostly unimodal and symmetric, then the following kind of empirical rule or rule of thumb applies here. And that's about, most of your observations, around 68% of them, about 2/3 will have z-scores between 1 and -1. So you can, if your observation is below the mean, your z-score will be negative. and about 2/3, most of your observations are within 1 standard deviation of the mean. Okay, and then the vast majority, around 95%, have z-scores within 2 standard deviations of the mean. Okay, so if you calculate your z-score, and most observations will have z-scores between 2 and -2. And so if you do encounter a z-score greater than 2, or a z-score more negative than -2, that would be considered unusual. Only about 5% of observations will have z-scores greater than 2 or -2. Okay, and then almost everyone, 99.7% of observations have z-scores between 3 and -3. So within 3 standard deviations above the mean and 3 standard deviations below the mean. And so if you do encounter an observation with a z-score above 3, or an observation with a z-score more negative than -3, that would be considered highly unusual. That's like, only 3 in 1,000 have z-scores, greater than 3 or more negative than -3. So that's those are some good kind of rules of thumb that you can apply. If your data is like really skewed, like you just have a whole bunch of outliers, this might not necessarily be true. But this is one way for you to kind of measure, what's unusual. And usually, anything with a z-score over 3 or -3, you would consider to be an outlier. Maybe even 2.5. Z-scores over 2.5, or more negative than 2.5. Okay. Another way for us to identify outliers or unusual observations is by creating box plots. Okay, box plots operate off of kind of the IQR. The IQR stands for the interquartile range. The interquartile range gives you the range of the middle 50%, your first quartile and your third quartile. First quartile is the 25th percentile. Third quartile is the 75th percentile. So I don't know, like when you were looking and applying to colleges, I think a lot of times colleges post their the range of the middle 50% of SAT scores. I don't know if that sounded familiar, but it would kind of just say like, 25th percentile to 75th percentile range for SAT scores is between here and here. And it kind of gives you a sense of like what the middle 50%, the typical range is going to be. Obviously, you're going to have some values of, the top few percentage will be, very high. And then, the bottom few percentages might be, comparatively low. You can kind of get a sense of like who's in the kind of middle 50%. And that's going to be your 25th percentile. So the spot where 25% of your data is less than or equal to your 25th percentile, or your first quartile, Q1, first quarter. And then Q3 is your third quartile, or your third quarter, 75th percentile. 70% of the data are equal to or less than or equal to the 75th percentile, or 3/4 of your data are equal to or less than your third quartile. So this is just a silly example where we measured how much several plants grew. So we got 14 measurements of plant growth, and here we have them placed in order from least to greatest. So some plants grew 3 millimeters, some grew 5 millimeters, some grew 7, 10 millimeters, 14 millimeters, 20 millimeters, 21 millimeters. And so we want to figure out kind of what is our IQR, and are any of these observations outliers? Okay. So the way we go about this is, well, first we find the median. I'm assuming you guys know how to find the median. It's just your middle value, right? So if you have 14 numbers, you got 7 below and 7 above. So our middle two numbers are 9 and 10. Okay, we got 1, 2, 3, 4, 5, 6, 7, which is at 9, and then counting 7 from the other side, we end up at 10. So our median is going to be halfway between 9 and 10, or the average of 9 and 10. Our median is 9.5, and we have 7 numbers below 9.5, 7 numbers above 9.5. So in R, you can take your numbers and you can just ask find the median of x, or in dplyr, you can just pull that variable and then say calculate the median or do summary median, and you get your median. So here I kind of just drew a line between 9 and 10. Median is 9.5. And then to find our quartiles, what I'll do is I'll take this lower half and I'll say, what's the median of my lower half? Okay, so here with the 7 values below the median, the middle number here is going to be this value right here. This is going to be my median. Okay, and then with the 7 numbers up here, my median is going to be this number, right? So I've got 3 below and 3 above out of these 7. So my first quartile is 7. Over here, my third quartile is 10. Okay, so my IQR is the difference between Q3 and Q1. I have an IQR of 3. My range would be the difference between the max and the min. I have a range of 18. The range is greatly affected by any kind of outliers. So if I do have an extreme value, like at 21 or something, or if this were to be 25, my range is going to be greatly affected. Whereas the IQR doesn't really care what's happening at the extreme ends. A useful thing is what's known as the 5-number summary. And the 5-number summary is your minimum, your first quartile, the median, your third quartile, and the maximum, right? And it's kind of like, on your gas gauge, you have like empty, quarter tank, half tank, 3/4 tank, and full tank, right? And the 5-number summary is kind of like those 5 locations, okay? Where is it at the bottom? Where's, a quarter of the way through? Where's halfway through? Where's 3/4 of the way through? And where's, the max, okay? That's going to be your 5-number summary. So our 5-number summary here would be 3 is the minimum, 7 is our first quartile, median is 9.5, 10 is our third quartile, and the maximum is 21. In R, if we have our vector of values, we can say summary of x, and this gives us our 5-number summary plus the mean. So we get the min, Q1, median, the mean, Q3, and the max. All right, and these match the values that we have. We can make a box plot. A box plot is a handy way for us to do a data visualization. And basically it's a visualization of the 5-number summary. And so box plots are by nature less detailed than histograms. And sometimes that's exactly what we want, okay? When you have less detail, it's easier to get the bigger picture, okay? So sometimes you just want to do quick comparisons, and you can do it with like a 5-number summary. And so the way we draw a box plot is we draw a box for Q1 to Q3, okay? Your box, you have a rectangle that goes from Q1 to Q3. Within that rectangle, you draw a line for the median, okay? So you're gonna get a rectangle with Q1 and Q3 as your boundaries. Inside, you get a line for the median. And then you get these lines that come out of the box. We call these whiskers. And they extend to the minimum and the maximum values in your data set, unless you have outliers, okay? If you have outliers, outliers get represented with dots. So what's an outlier, okay? Well, we have these invisible boundaries called fences, the upper fence and the lower fence. And basically you take your rectangle, your box, and you go 1.5 rectangles above and 1.5 rectangles below, okay? So the upper fence is 1.5 IQRs. IQR is basically the width of the box, right? And you go 1.5 rectangles above, and you have kind of this boundary, this invisible boundary between what the box plot would consider to be outliers and what is not considered to be an outlier. And then you go 1.5 rectangles or 1.5 IQRs below, and that's going to create this invisible boundary between what the box plot would consider an outlier or not. So if we visit our same data here, okay, I have an IQR of 3. 1.5 IQRs is 4.5, 4.5. Okay, so I'm going to do 7 minus 4.5. All right, and my lower fence is going to be at 2.5. So I do 1.5 IQRs below Q1. So 7 minus 4.5. This is 2.5. I say, do I have any values in my data smaller than 2.5? I don't. Okay, so I have no outliers on the lower side. The smallest value I have is 3. That's above my lower fence. I don't have any outliers there. Okay. If I start at Q3 and I go 1.5 IQRs above, that takes me to 14.5. Do I have any values greater than 14.5? Yeah, I do. 20 and 21 are greater than 14.5. So these two values are considered outliers. So I have 2 outliers on the upper side. Okay. And then so now box whiskers will extend from the box to the smallest value and the largest value in my data that aren't considered outliers. So I'm going to get lines going from 3 to 14. Okay, so so in R, this is how you would do a box plot. You know, here are my values. I'm going to throw them into a data frame, and I say, okay, make a ggplot for my data. I'm going to put map values to the x-axis, and I say geom box plot. Okay, and with geom box plot, okay, we see we have a box, the rectangle. It's like a really, really thick rectangle, but the box goes from 7 to 10. Okay, and I have a line in the middle at 9.5. Right, and then I have a whisker going from the box down to the smallest point in my data, which is 3, and I have a whisker going from Q3, 10, up to the largest point that's not an outlier, which is 14. Okay, and then the values 20 and 21 are represented with dots to indicate that they are outliers. Okay, so so basically I'm going 1.5 rectangles above to 14.5. That's my upper fence there. Does that kind of look okay regarding the box plot here? And so this is how box plots would determine and say these are your outliers here. Okay, here's a box plot looking at, say, the penguins data for bill length. Okay, so here you can take your box plot and you can specify a grouping variable like species to one of the axes. So here I'm going to say bill length goes on the x-axis, and then on y we're going to put species. Okay, and you can see, all right, here is the your middle 50%, Q1, the median Q3, and this is the largest value that's not considered an outlier, is something around 50. If this is 50 and this is 60, this is like 56, something around there. And we do have one outlier in bill length for Gen 2 penguins, and that would be something with like a bill length of like 59.5. We only had one Gen 2 penguin with a bill length that long. Okay, whereas the other species of penguins, we don't have any outliers there. We do have variation. Okay. And 50% of penguins are within this box, right? And so one thing to note about the box plot is you have 25% of penguins are between this line and this end of the box, okay? And I've got 25% of penguins above this thing, right? So we have the same number of penguins from this line to here as we do from here all the way up to here, okay? And then I got a quarter of my penguins go from this line down to here, which is the same number as between here. So I got a quarter of the penguins right here, quarter of the penguins here, quarter of the penguins between here and here, this small little band, and a quarter of the penguins over here, right? Same thing with the Adelaide penguins. A quarter of the penguins from here to here, quarter of the penguins from here to here, quarter of the penguins from this line to this end of the box, and a quarter of the penguins from here to here, right? So the box plot kind of splits your data up into into your 4 quarters, as indicated by the the locations here. And then anything that's considered unusual gets plotted as dots. Any of these outliers are dots here. Okay. So so this is just a way for you to kind of look at, maybe one variable at a time and identify if anything's unusual. And you might have different observations with different variables, and you might want to compare them and say, all right, is this one more unusual or is this one more unusual? You can use z-scores as a tool for that, and you have a couple of these visualization things. All right, let me give you your last view quiz answer, which is the letter C. C as in cat. C as in cat is our third view quiz answer. Okay, we'll end here for today, and we'll see you on Friday.